In this problem, we're going to apply, or try to apply, initial value theorem, final value theorem to know what's happening to the initial value of f and the steady state value of f, given big F of s. So again, we have it presented here in a factored form and a non-factored form already. So first, let's see, can we even apply initial or final value theorem? So we have to check the poles of s times f of s. So that is going to be s times, I'll use the factored form for this, 3s plus 4, and we have an s squared plus 2s plus 4. Right, so we see here that the s on top, the s on the bottom are going to cancel each other out, and I can rewrite this as 3s plus 4 on the top, and then s squared plus 2s plus 4 on the bottom. And we want to know the poles of this system. Now, if we go through the denominator, and ideally we would be able to factor it, and then it's really easy to know what the poles are going to be to find what makes the denominator 0. But in this case, it is not factorable. There's no integers that we can have s plus something, and factor it. And in fact, not only are they not integers, but the poles of this system are not going to be purely real. This is a case where we would use something like the quadratic equation to find the poles of this system. So the poles of this system, I'll call them P here, we have two of them because it is quadratic. And if we go through the quadratic equation, we find that the poles are going to be -1 plus or minus j root 3 to have the exact values there, which we would get using the quadratic equation. So -1 plus j root 3 and -1 minus j root 3 are the two poles of s times f of s. So a couple of notes here. I am using j to signify the square root of -1 rather than I, and I will carry that through most of the course. There might be times I use I by mistake, but typically I will be using j to designate the square root of -1, because that way it is going to be harder to confuse if I used I. We're going to be using that for current when we have electrical systems. So j is going to be a better variable or a better symbol to use for the square root of -1, so we don't have that confusion. But I and j for square root of -1 are interchangeable. And looking at these poles, what we're checking for is stability. Are all poles, in this case both poles, in the left half plane? Well, let's see. All that matters to be in the left half plane is the real part of the poles. And both poles have a negative real part, -1. So yes, this is stable. Both poles are in the left half plane here. It's just that they're complex rather than other examples we looked at where they were purely real. So that means that, again, we can use initial value theorem, final value theorem, even though the poles are complex. So let's see what is our f of 0 and using initial value theorem. So f of 0, we can take the limit as s goes to infinity of s times f of s. So that's the limit as s goes to infinity of, and when I'm taking the limit as s goes to infinity, I want the unfactored form here. So that's going to be 3s plus 4 over s cubed plus 2s squared plus 4s. And I forgot to put that s on top. So 3s squared plus 4s is going to be on the top. Again, because it's s times f of s. So I multiplied my f of s by s, so it raised the degree of every s in the numerator by 1. I chose to represent it that way. All right, so we have our variable going to infinity. We have a polynomial in the numerator and the denominator. But looking here, the numerator is of degree 2, the denominator is of degree 3. So the denominator is of a higher degree, so our rule is going to be that this will always go to 0 then. So our initial value is that this f of t, when time is 0, is going to have initially a value of 0. And the steady state value is going to be the limit then as s goes to 0 of s times f of s. And I already have sf of s, and here I'll use the factored form, although really it's not that factored anymore. 3s plus 4 over s squared plus 2s plus 4. So that same term I used that I found the poles of. And we already know that there's no pole at 0, so there's no problem in just simply making s equal to 0. That's still going to work for us. So if we do that, 3 times 0 is 0. We're left with 4 on top. And in the denominator, we have a 0 plus a 0 plus a 4. So we have 4 over 4, or 1. So steady state value of f of t, it's going to be 1. So f of t is going to start at 0. Eventually, it's going to take a value of 1, and it's going to do something in between, which this doesn't tell us what that does. In Unit 2, we're going to get that information out of it. And in fact, it's going to be really important to know what happens in between, to know what the poles of this system are, because the poles are going to tell us about what's happening in between the initial value and the final value. But more of that in Unit 2.